Pleasure to welcome, and it's my pleasure to welcome all of you on behalf of ESA, the International Space Science Institute in Bern, Switzerland, to today's talk in ESA's Game Changer series. I'm Joachim Bamskans, Director for Astrophysics and Cosmology at ESA and your host today. By now, most of you are regular participants at ESA's online Game Changer seminar series, which we introduced about a year ago in July 2020 on game-changing missions, because physical meetings in Bern were not possible anymore. After a short break in April, we restarted in May with talks focused on scientific questions, and we will have a talk every Thursday until the summer break. In next week's seminar, Sabani Basu from Yale will talk about, do we know what the sun is made of? The puzzle of the solar composition. In case you missed any of our previous talks, they were recorded and are available on the ESA website. We are very happy to welcome today Eva Grebel as our speaker. Eva studied at Bonn University, and she spent 2 years as an ESO student fellow at ESO in Chile. She was a postdoc at the University of Illinois in Urbana-Champaign, at Würzburg University, at UC Santa Cruz. Then she won a Hubble Fellowship, which she spent at the University of Washington in Seattle. In 2000, Eva returned to Europe as a research group leader at the Max Planck Institute for Astronomy. In 2003, in fact, Eva moved to Switzerland and became a professor at Basel University, and a few months later, she became the director of the Astronomical Institute there, succeeding Professor Tammann. Since 2007, Eva is a professor at Heidelberg University and the director of the Astronomisches Institute. Eva Grebel leads a collaborative research center, Sonderforschungsbereich, on the Milky Way system, which is funded by the German Research Foundation, DFG. She has received a number of scientific awards for her work on galactic archaeology. She's a member of the Heidelberg Academy of Sciences, of the Hector Fellow Academy, and of the German National Academy of Sciences, Leopoldina. Now the screen is yours, Eva. We are looking forward very much on an exciting talk on the merger history of the Milky Way, what Gaia revealed. Please.
Thank you very much for this very nice introduction and also for the invitation. I'm very happy to be able to talk in this Game Changer series at the ESA. So my topic today is the merger history of the Milky Way, with particular focus on what Gaia revealed. You will find that many of the publications that I'm referring to are very recent publications, because essentially all of this is extremely recent. It is actually ongoing research. The picture may continue to change in the coming years, but Gaia has already led to major breakthroughs that would not have been possible with the traditional methods that were in place before Gaia flew. You know, traditional methods to study the merger history of the Milky Way, which relied, for instance, primarily on photographic or photometric surveys with CCD cameras, as well as spectroscopic surveys. Those, however, remain very important, and they essentially augment the excellent data that we get from Gaia, especially the high quality astrometry that Gaia is delivering. All right, so with respect to the merger history, let's first take a look at the current cosmological picture. What do we expect based on up-to-date cosmological models? Well, the paradigm is essentially that galaxies show hierarchical structure formation, that larger structures form through successive mergers of smaller structures. And here on the left-hand side, you see snapshots from one big cosmological simulation, the illustrious simulation, where we have dark matter only in the leftmost panel. That's what you see here in blue. And then we have here a simulation that includes also, or a part of the simulation that also includes baryons. In particular, what is shown here is the gas density and how it evolves as a function of redshift, going from early structures where we have just a few density concentrations to a universe that becomes gradually more and more structured as the effects of gravity set in, with some counteraction from effects of feedback, star formation, supernova explosions, and so on and so forth, which then may redistribute the baryons that previously fell into the gravitational potential wells of the dark matter halos and in part are now blown out again. So overall, we have a picture in which large structures form through successive mergers of smaller structures. And that also means that observable signatures of past merger events may in fact be retained. So in particular, speaking as an observer, smaller structures such as dwarf galaxies are then important building blocks of more massive galaxies. And this process, this entire scenario is potentially traceable, especially in galactic halos, where the kinematic signatures and also overdensities caused by such merger events should be observable over long periods of time. Moreover, the surviving small structures, the surviving dwarf galaxies, can be considered fossils of galaxy formation and evolution. Here you see another depiction of the cosmological picture, a so-called merger tree. This tree is one that grows from the top to the bottom, so it grows in this direction. Up here we have the smaller structures, essentially the branches which now merge and form thicker and thicker structures all the way to the trunk, which could be then one very massive galaxy or actually even a galaxy cluster. So that is the cosmological picture. We expect to have had multiple merger events in the buildup of more massive galaxies, such as our own Milky Way. And if that happens, then satellites get disrupted, satellites will get accreted. Here you see snapshots from yet another simulation. This is now just an N-body simulation where we have an edge-on spiral galaxy and a small satellite. The small satellite now falls into the gravitational potential well of the more massive galaxy, and while it orbits and while it experiences the changing tidal forces from the massive galaxy, gradually stars get removed from this smaller galaxy. They become unbound, they form extended tidal tails, and eventually the entire dwarf galaxy gets disrupted. And with these tidal tails that you can see here, it gradually becomes accreted by the more massive galaxy. Such satellite disruption may lead to the tidal stripping of up to 90% of the original mass of the satellite, the original stellar mass in particular, that may be lost, but the remnant of such an event could in principle survive. It could also happen that we have complete disruption and ultimately satellite accretion. And when accretion happens, then more massive satellites will experience higher dynamical friction. They sink more rapidly to the inner regions of the more massive galaxies. We know that galaxies obey a so-called mass metallicity relation, in the sense that more massive galaxies are more metal rich. That would mean that if more massive satellite galaxies sink more rapidly to the central regions, they will contribute more at the higher metallicity end to their new host galaxy than low mass satellite galaxies, which will be of low metallicity to begin with. So due to the mass metallicity relation, we expect that more metal-rich stars end up at smaller radii. If you have multiple accretion events of this kind happening over the lifetime of a galaxy, and if you look at the resulting tidal streams that you would expect, which here are color-coded, each color corresponds to a different disrupted satellite, you would expect that the outer regions of such a more massive galaxy in particular will show a highly substructured shape, and we see still remnants of such accretion events, which in part may survive over extended periods of time. So that's the expectation. We should be able to find observable signatures. Furthermore, then the cosmological scenario tells us that the stellar halos of more massive galaxies are composed in part of accreted stars from smaller satellites, but also in part of stars that formed in situ. One could also say halos grow from inside out. In the outer regions, it's primarily accreted. In the inner regions, it's primarily in situ at location star formation. And that you see here in two images of a cosmological simulation that show, on the one hand, the in situ stars, which are strongly concentrated around the massive host galaxy in the center. And here you see the accreted stars, which fill a much larger volume and show much more substructure as compared to this smooth structure of the in situ stars. Cosmological simulations also suggest that we would expect a wide variety of satellite accretion histories we may have relatively smooth growth, we may have discrete events. Generally, the expectation is that of the order of 5 relatively luminous satellites with stellar masses of maybe 10 to the 8 to 10 to the 9 solar masses are the main contributors to stellar halos. And that these kinds of objects should have merged maybe 9 billion years ago or longer ago. They may have contributed in particular to the buildup of the inner regions, in particular also the inner halos of more massive galaxies. More than 9 billion years ago, if that is the time at which most of the mergers happened, if you translate that into redshifts, that would mean satellite accretion of this more massive type is expected to have happened mainly between redshifts of 1 to 3. And here we see another cosmological simulation that now shows us the age distribution as a function of galactocentric distance of a massive host galaxy for the in situ stars. And what we can see here also is we expect that a lot of in situ star formation happened already early on, but in a disk galaxy like the Milky Way, where we have still ongoing star formation in the disk, we expect that that continues until the present day, as can also be seen here in this diagram, where we have age versus galactocentric distance. If instead we look at the age distribution of the accretion events, we find that most of these more massive accretion events are predicted to have happened at early times, and also, again, they fill a much larger volume. Furthermore, not all objects that get into the potential well of a massive galaxy get accreted right away. Some can survive over extended periods of time, or maybe they fell in only more recently. And if you wish, you could say that these two lines of satellites that are not yet disrupted may correspond to first order to the Magellanic Clouds. So now let's switch to the observational side. That was the cosmological picture. Can we find remnants of massive accretion events in our own Milky Way? In fact, the first and rather spectacular finding of that case happened long before Gaia. That was the discovery of the Sagittarius dwarf spheroidal galaxy, which was published by Ibata and collaborators in 1994. In the lower part of this slide here, you see an infrared image obtained by combining two mass data of our Milky Way. So we nicely see here the disk of the Milky Way, relatively unobscured by dust. There are some dust features visible. We see the bulge of the Milky Way. And we also see that the Milky Way is surrounded by two rather luminous satellites, which can be seen in this infrared image. Those are the Magellanic Clouds, two actively star-forming and rather gas-rich satellites. Furthermore, when you look very, very closely, and now I don't know if it's really going to be visible for you, but if you look very closely, you may be able to see that there's a slight density enhancement or luminosity enhancement here in this region. That is actually the locus of the center of the inner region of the Sagittarius dwarf spheroidal galaxy that was discovered in 1994. It was not discovered in two mass images. They did not exist at that time. It was not discovered in the infrared. It was discovered actually in the optical. And this inset up here actually comes from the original press release, where we see the dense central part of Sagittarius. And there are several globular clusters associated with it. 4 are marked here with these star symbols. It was hypothesized at the time of discovery that this might be a disrupting dwarf galaxy, in which case one would expect extended tidal tails extending in these two directions here, which then would lie roughly along the orbit of that galaxy. And indeed, searches that began right thereafter by many different groups revealed the all-sky distribution of much of these tidal tails in the coming years using major photometric surveys. And this has continued until the present day. Today, we have the advantage of being able to use also Gaia data. And Gaia data now provide us with not only the option of detecting overdensities on the sky, like in photometric surveys, but Gaia also gives us all sky proper motion information. So now we can actually see in which directions these stars are moving. And in fact, there were all sky proper motion searches conducted for Sagittarius members recently published by Antocha and collaborators. In addition, one can use the Gaia distance estimates, parallaxes for instance. Moreover, one can focus on special types of stars, such as periodic variable stars. Lyrae stars are one such type. Lyrae stars are traces of old populations. They have very regularly varying light curves. Since Gaia observes the sky repeatedly, and you've heard about that in past talks in the seminar series, one is able to get light curves from Gaia observations. The light curves tell us also something about the distances of the underlying stars. So our Lyrae stars, as tracers of old populations, can be used as tracers of old accretion events. And Sagittarius has been traced in our Lyraes across the sky. Moreover, if one combines the kinematic information with from spectroscopic information, from spectroscopic surveys in part, which provide radial velocities, with the kinematic information from proper motions that Gaia gives us, as well as the position and distance information, one obtains a 6-dimensional view. One can add in additional dimensions, for instance, chemistry, that would give us a 7-dimensional view. And that provides then improved all-sky tracking of the tidal stream of Sagittarius, its distances and its motions. In particular, Gaia has led to improved models of the orbit of Sagittarius, which in turn can be used to obtain improved estimates of the Milky Way's mass, the halo shape, the orientation. And one is even able now to see evidence for the impact of the Large Magellanic Cloud on the motion of the Sagittarius dwarf swirl, which is currently being accreted, which in fact suggests that the Large Magellanic Cloud is relatively massive. What you see here is an all-sky distribution of the Sagittarius stream. This is the dense center, which was already discovered back in 1994. This here is the leading arm of the tidal tails of Sagittarius. This here is the trailing arm, and you can see that it has been traced over much, much larger distances and much larger volumes. The stripping time here is indicated up here. It's color-coded in gigayears, both for the leading and for the trailing arm. So Sagittarius has been around for many gigayears as a member of the Milky Way. Sagittarius was a very impressive, relatively massive accretion event onto our Milky Way. Gaia has enabled the discovery of an even more massive, more important accretion event, which would not have been possible without Gaia, the detection. And this accretion event has been dubbed Gaia-Enceladus or Gaia Sausage. For instance, this accretion event is visible in very deep color magnitude diagrams as obtained by the Gaia satellite. Here you see a region, a color magnitude diagram corresponding to a region of only halo stars, stars kinematically selected to have tangential velocities greater than 200 kilometers. And interestingly, this color magnitude diagram now shows two sequences, a redder sequence and a bluer sequence. The redder sequence is interpreted as being due to a heated, hot, thick disk of our Milky Way. And over here, for the bluer sequence, we see essentially what we expect for the more metal-poor halo. Now, when you look at this photometrically, you can ask yourself, where are these stars located when instead we look at the 3-dimensional velocity space? And one such projection is shown over here, the so-called Tumor Diagram, where we see stars that are in the immediate vicinity of the sun, the thin disk stars essentially being located over here. And then with increasingly deviating velocities, we slowly move towards stars in the thick disk and in the halo. Over here, we have the locus of the hot thick disk. Over here, a locus of stars, a blob of stars was identified, which has been called Gaia-Enceladus. It has been identified as a major merger event that happened in our Milky Way early on, about 10 billion years ago, and that contributed more metal-poor stars to the Milky Way, which do not follow the overall typical galactic rotation. And in fact, a large portion of the stars that we usually consider inner halo stars come, in fact, from this Gaia-Enceladus structure. This is taken from the press release, from the Gaia press release that came out when the discovery was made back in 2018. And quoting from this press release, Gaia discovered a large number of stars moving along elongated trajectories in the opposite direction to the majority of the Milky Way stars. The motions of these stars are indicated by the little yellow arrows. Also, it was found that these stars have a different chemical composition, namely a lower heavy element content, a lower metallicity than the stars of in our Milky Way. And that has been further confirmed in a variety of studies. Here you see metallicity distribution functions and age distributions obtained by Gaillard and collaborators who followed up on the stars in Gaia-Enceladus, and they found these stars are indeed more metal poor in their overall metallicity distribution. And you see that indicated here, this blue regime, these blue histograms are stars from Gaia-Enceladus. These are stars of comparable stellar populations in the Milky Way, which are more metal rich. Moreover, these stars in Gaia-Enceladus are on average rather old. And in fact, they tend to be older than the thick disk. So what you see here is another press release image of the distribution of the stars in parallax space. The Gaia-Enceladus structure also contributes a number of globular clusters whose position is indicated by these white filled circles, as well as, of course, variable stars such as our library stars. It has been inferred from these Gaia data that at the time of accretion, actually, this was a 1:4 merger, so a mass ratio of Gaia-Enceladus to the Milky Way of 1:4. That Gaia-Enceladus progenitor was a bit more massive than the small Magellanic Cloud. It had a virial mass of about 10 to the 10 solar masses. The stars that it contributed are as old as the old Milky Way stars, but have a lower metallicity. And it is also believed that this merger may have formed the inner halo and the thick disk of our Milky Way. Our Milky Way has a complex disk with an old metal poor or more metal poor thick disk that has larger scale heights, that has a higher random component in its rotational motion, as well as a young thin disk. Furthermore, Gaia-Enceladus is believed to have contributed at least 27 globular clusters to our Milky Way. We can use chemical information in order to further constrain the properties of the progenitor of such a merger event. The cartoon that you see here on the left-hand side is just a general cartoon to show how chemical evolution in galaxies proceeds, and you can use certain element abundance ratios as indicators, as essentially diagnostic indicators, in particular the metallicity, Fe/H, ion abundance along this axis, where solar abundance is located at 0. This would be 1/10 of solar abundance, 1/100 of solar abundance, and so forth. It's a logarithmic scale, essentially. And so-called alpha elements. Alpha elements are those that are formed by the capture of helium nuclei. Alpha elements include, among others, magnesium or calcium. And those kinds of elements show a relatively flat trend across a wide range of metallicities for a time in which only massive stars contribute to the chemical enrichment. Massive stars that will lead to the formation of supernovae of type 2. So as long as we have only contributions from supernovae of type 2, from massive stars, the chemical enrichment, which happens shortly after stars form, we end up with this plateau where we have increasing metallicity enrichment, but constant alpha/Fe and relatively high values of alpha/Fe. After approximately 1 billion years, when also lower mass stars become appreciable in their contributions to the chemical enrichment, in particular, white dwarfs that turn into supernovae of type 1a, we actually see a turnover. We see a knee here in this plateau. We no longer have a plateau, but we go to lower alpha/Fe ratios because now alpha elements are no longer produced by these supernovae of type 2. In particular, they just lead to metallicity enrichment, to ion enrichment. And the length of this plateau tells us something about for how long massive star formation was the primary contributor to the chemical enrichment. It tells us something about the efficiency of star formation If the turnover happens already at low metallicities, it tells us that we had slow enrichment, low star formation rates, possibly loss of metallicity due to winds. So heavy elements that were formed in stars and ejected were lost from the galaxy due to winds. Here, where we have a long plateau, we have fast enrichment and a longer period before supernovae of type 1a become effective. These kinds of diagnostic plots can then be used to constrain the properties of progenitor stars. For dwarf galaxies, we tend to have an early turnover, slow enrichment. For massive galaxies like the Milky Way, we tend to have an extended plateau before the turnover happens at higher metallicities. So with these kinds of diagnostics and chemical information, one can then look at different populations believed to have formed either in our Milky Way or in dwarf galaxies. And here you see a distribution of stars selected by metallicity and orbital eccentricity, namely whether they have almost circular orbits or more extended elliptical orbits, as well as their alpha over Fe content marked here by magnesium for different components. And the green component that you see here is actually the component associated with Gaia-Enceladus. The yellow component could to first order be considered to be the thin disk, and the red component here is the heated thick disk or the in situ halo. And the alpha over Fe ratios that were measured in these stars in Gaia-Enceladus suggest that in fact Gaia-Enceladus, or the progenitor of Gaia-Enceladus, was a lower mass dwarf galaxy where chemical enrichment was not as efficient as in the in situ stars in the Milky Way. The low alpha over Fe and the high eccentricity stars are slightly younger than the majority of the high alpha over Fe sample that we see in the in situ stars. And the ages in this case come from astroseismology. So Gaia information was connected to Kepler astroseismology. Kepler is an astroseismology satellite to obtain accurate age dating. And that suggests actually that much of the in situ high alpha population, the so-called heated thick disk or in situ halo, was already in place before the accretion event of Gaia-Enceladus occurred. It's a way of trying to constrain the time at which the accretion happens. The lower age limit is 9 billion years, more likely a little bit earlier than that this accretion happened. So Gaia-Enceladus is a very spectacular event that was discovered just in Gaia data recently. Another discovery that has just been announced and that may indicate an even more massive accretion event is the so-called intergalactic structure, or IGS, that was found using Gaia distances, apogee chemical information from spectroscopy and Eagle cosmological simulations. Here, Horter and collaborators suggest that there is an accreted metal pore structure within the inner 4 kiloparsecs of the Milky Way, and that this metal pore structure was accreted early on, that it may have been twice as massive as Gaia-Enceladus, that it may have possibly been the most massive accretion event onto our Milky Way, with a ratio of a mass ratio of 1 to 3 or even 1 to 2 in the early Milky Way. And metal poor in this case really means relatively low metallicity, even more metal poor than Gaia-Enceladus. It is believed to have happened potentially somewhat earlier than the Gaia-Enceladus accretion event. Gaia-Enceladus may have been the last massive accretion event. I'm not going to go through all these chemical diagnostic plots that are shown here. People, Horter and collaborators, use both chemistry as well as dynamics in order to identify this metal poor component, which is shown here in yellow in this histogram of metallicity distribution functions. So relatively metal poor stars contributed by this presumed accretion event that is called the intergalactic structure. That is perhaps the most massive accretion event that we know of so far that contributed to the buildup of our Milky Way, possible only in detection thanks to combination of Gaia data with ground-based spectroscopic surveys. So what impact do such mergers have on the Milky Way? Oh, let me add, there are additional comparatively massive accretion events that have been discovered that I have not mentioned here. Sequoia, for instance, or Thamnos, and they also contribute, but they were of lower mass than Gaia-Enceladus and the supposed galactic inner structure. So what impact do such massive mergers, comparatively massive mergers, have on our Milky Way? Let's consider, for instance, Sagittarius. The center of Sagittarius is currently about 18 kiloparsecs behind the bulge of the Milky Way. Sagittarius shows a leading and a trailing arm. It has an extended star formation history. It shows an age-metallicity relation. It contributes a number of globular clusters. The total mass early on was presumably of the order of 2.5 times 10 to the 10 solar masses when it merged with the Milky Way. And it is believed to have interacted with the Milky Way disk since 6 or 7 billion years in the past. The first real infall onto the Milky Way happened probably 5.5 billion years ago. This impact, or this infall, had of course a major impact on Sagittarius. Sagittarius was quenched. That means gas from Sagittarius was removed, star formation was inhibited. However, the infall of Sagittarius also triggered star formation in the Milky Way. And in fact, a recent study of stars in the solar neighborhood has revealed that there are multiple peaks in the star formation history in the disk of our Milky Way, which are correlated with pericentric passages of Sagittarius, when Sagittarius had its closest passage in the past with the Milky Way disk. And that appears to have triggered every time star formation in the Milky Way disk. So Sagittarius has also had an impact on the Milky Way's disk in terms of affecting its star formation. Furthermore, a study of the kinematics of stars in the solar neighborhood in a very, very thin annulus actually around the sun has revealed that there is substructure that has been described as a snail-like structure or a spiral-like structure, which you can see here in a space spanned by position and velocity. This spiral, I think, is clearly visible in this binned diagnostic diagram. This has been interpreted as being due to oscillations that were triggered in the disk due to the interaction with the Sagittarius dwarf galaxy. When we have a disk crossing mass, it will drive spiral arms and vertical wave-like responses in the disk. Moreover, simulations that were done then suggest that the present-day mass of Sagittarius is actually not high enough to have triggered this spiral distortion or spiral perturbation, but that Sagittarius triggered this several billion years ago, and that it is experiencing still rather substantial mass loss while it is being accreted onto the Milky Way. That is at least the idea of one of the simulations that try to explain this phase spiral, as it has also been called. Again, a discovery that was only possible thanks to Gaia data because they provide the required phase space information. Another distortion in our Milky Way due to interactions with companions is the warp in the Milky Way's disk. Actually, our Milky Way's disk is not plain as one might expect, but it shows a warp, it shows a distortion. This distortion has been first found independently of Gaia in H1 data, so in cold gas data observed in the radio. It has meanwhile also been traced in stars, including Gaia Cepheids. Cepheids are relatively young, massive, regularly pulsating stars that were found in the repeat observations of Gaia. They have been found across the entire sky. These data have been used to map the warp of the Milky Way's disk. And you can clearly see here, we have always plots that go from the center of the Milky Way further out. So this is radial direction, and this is height below or above the plane. Normally, if you have a plane disk, you would expect that this gives you a straight line as a function of radius. It does not. It actually nicely shows you the warp in the disk. And that has been done with data from the oval survey, which is an extensive survey for variability, photometric survey, as well as in the infrared. And there, Gaia data could not be used anymore because of too high an extinction in the infrared, in the part of the disk that is usually invisible to us because of dust, with the VVV survey by Decani and collaborators. So the warp of the disk has now been traced across a large portion of the sky and is believed to be due to the interaction with Sagittarius and probably the Magellanic Clouds. There are different models that attribute it to interactions with either one or both of these massive, relatively massive satellites. The Large Magellanic Cloud and the Small Magellanic Cloud are falling into the Milky Way, its potential. You see them here in this all-sky distribution marked by this bigger star and the smaller star. That's the center of the Large Magellanic Cloud and the Small Magellanic Cloud. They have not yet merged with the Milky Way. They may do so in the future. However, their motion around the Milky Way and their mass is already having an effect on the Milky Way. Namely, there's a wake that one can observe at halo star distances between 60 to 100 kiloparsecs. So there are overdensities triggered here in the halo star distribution due to the motion, the orbital motion of the Magellanic Clouds. So again, an effect that satellites can have when they interact with a more massive galaxy. Now, another interesting point about accretion and merger history of the Milky Way is globular cluster accretion. I already mentioned that a number of globular clusters were contributed by the Sagittarius dwarf swaddle galaxy when it merged, as well as by the Gaia-Enceladus galaxy. And here we see an image of one of the remaining unimpacted dwarf galaxies around the Milky Way, the Fornax dwarf swaddle galaxy. Fornax actually contains 5 or possibly even 6 globular clusters. One such globular cluster is this little point that you see over here. Additional ones are distributed throughout this image of Fornax. If Fornax were to merge with the Milky Way, it would contribute all of these globular clusters to the Milky Way. And we may now ask how many of the Milky Way's globular clusters come actually from accretion events. And here you see a plot that is pre-Gaia. This plot looks at the age metallicity relation of globular clusters. For globular clusters, since they are nearby and in our Milky Way, we can obtain fairly accurate ages thanks to deep color magnitude diagrams. And we can also measure their metallicities spectroscopically. When doing so, we find that in a diagram of age versus metallicity, globular clusters basically fill a rather wide space. And it has been suggested now that if we compare that with the age metallicity relations of different types of galaxies, in particular of dwarf galaxies, it may tell us something about the origin of these globular clusters. You see these age metallicity relations, which basically mean that metallicity gradually gets enhanced as a galaxy continues to evolve and continues to form stars. These age metallicity relations actually coincide for some of the more metal-poor globular clusters. So for instance, for the NMC, for the SMC, for the dwarf irregular galaxy Wolf-Lund-Mark-Melot, suggesting that perhaps the more metal-poor globular clusters come from a host galaxy that had a lower metallicity to begin with, and that the more metal-rich globular clusters that we see over here at the same age were formed in situ in our more metal-rich Milky Way. So it's a suggestion, just based on the age metallicity relation, that the more metal-poor globular clusters might have been accreted. And indeed, we know that Sagittarius contributes or has contributed several globular clusters, potentially up to 9 globular clusters. The nucleus of Sagittarius is a dwarf galaxy, is a star cluster itself, a globular cluster. The nucleus of Sagittarius is located over here in this little cartoon. These globular clusters, as well as intermediate age clusters, also follow their own age metallicity relation, and that is corresponding to what you would expect based on the mass of this lower mass dwarf galaxy. So Sagittarius seems to have contributed. Moreover, Gaia-Enceladus has contributed, as we saw already earlier. And we have had about 5 relatively massive dwarf galaxies that were accreted by the Milky Way. It's believed that they contributed up to 50% of the globular clusters of the Milky Way. They only contributed about 10 to the 9 of the solar masses of the stellar mass. so a relatively low amount of stellar mass, but quite a few globular clusters. And there may be at least 11 additional globular clusters from lower mass dwarfs. And these statements are based on Gaia kinematics, on HST ages obtained with the Hubble Space Telescope, spectroscopic metallicity, measurements, integrals of motions. It is one suggestion that has been published in the literature. There are other scenarios where some of these globular clusters are being associated with other dwarf progenitors. So this is not the final answer yet, but it does look as if a major portion, possibly as many as half of our globular clusters, come from merger events. Furthermore, we know that globular clusters themselves will get disrupted as they orbit the Milky Way. Most of them can survive over extended periods of time, over more than a Hubble time, but some may get disrupted when they experience a varying gravitational field as they orbit the Milky Way. For instance, when they pass through the disk or near the bulge, and that may lead to the dissolution of globular clusters, leading to these extended tidal tails. And if some of the globular clusters actually come from dwarf galaxies, that means it's yet another way of contributing external stars to the field populations in our Milky Way. It has been estimated in some of our work that up to 11% of the halo field stars originate from globular clusters. And since my time is approaching its end, I think I might skip this or make it very quick about satellite planes. You may have heard that the satellites around the Milky Way are not randomly distributed, but they seem to lie along preferential planes in the sky. And that is an interesting observation that has already been known long before Gaia. It dates back to the early work by Kunkel and Demers in 1976 and Lindenbell in 1976. The new discoveries of satellites that happened in recent years have further supported this picture. We still see relatively thin planes along which satellites seem to be located. But one of the big questions is, are these kinematic planes? Does it mean that the satellites are actually orbiting along these planes? And if so, why? Gaia has helped to refine this picture. Thanks to Gaia, it was possible to obtain orbits for these satellites around our Milky Way, not for all of them, but for many of them. One can then orbit backwards or integrate backwards what these orbits would look like. It turns out that some satellites do seem to be associated kinematically with these planes. In other cases, their location is fortuitous. It also seems that these planes are not long-lived structures, but will eventually dissolve or look rather different in the longer-term future. And some satellites are actually co-orbiting. Some are moving essentially in the opposite direction, so counter-orbiting. It looks as if overall, and that is now also supported by cosmological simulations, what we see here is actually an impact of infall of satellites along cosmological filaments and dwarf group infall into the potential wells of more massive galaxies, such as the Milky Way. For instance, the infalling large and small Magellanic clouds appear to be bringing in at least 4 more very faint satellites, very faint dwarf galaxies, possibly even more. In studies with Gaia proper motions to obtain orbits for these are still going on and continuing. So we talked about relatively massive merger events so far. I would like to show you that there are also many, many more numerous smaller merger events that contributed to the buildup of the Milky Way. And these we see primarily in the halo, where such structures can be more easily recognized. They were already discovered in part long before Gaia, thanks to photographic and photometric surveys. With Gaia, however, we also have the kinematic information, and we can really find many new streams across the entire sky. Here, I show you the distribution of several of these discovered streams. Sagittarius is this very big feature that you see here. Then you see many smaller, more narrow streams from the review paper of Amina Hilmi from 2020. Many of these narrow streams probably had low mass satellite progenitors and were accreted relatively early on. And that search for streams is still continuing. Some streams come from disrupted globular clusters, as one can also show when adding chemical information, because then all stars would essentially have the same metallicity. Others show metallicity spreads indicative of an origin from dwarf galaxies. And here you see very recent results from Gaia Early Data Release 3, a paper by Ibata and collaborators, where they looked for streams at different distance intervals. This is the distance interval of 3 to 12 kiloparsecs from the galactic center, here 10 to 30 kiloparsecs from the galactic center. You can see that our Milky Way is filled with streams which in part have names, which in part actually come from globular clusters, but in part they come from disrupted dwarf galaxies. In many cases, their progenitors are not yet even known. And these kinds of studies will continue in the coming years and give us a much better idea of how many low mass satellites have contributed to the buildup of the halo in particular. And in some cases, we can then follow up on these streams, again, including Gaia data, as well as, for instance, also spectroscopic ground-based information. We find many very narrow streams. We find even substructures such as these gaps in these streams. It has been hypothesized that some of these gaps in very narrow streams may actually come from interactions with small dark matter halos, which have been theoretically predicted but are unobservable, but that if such small dark matter halos pass through narrow streams, they would create gaps. So it's a hypothesis that still needs to be verified. There are different opinions in the literature, but furthermore, these streams also allow us to constrain the galactic potential because, of course, these satellites that are being disrupted or globular clusters that are being disrupted orbit in the gravitational potential of our Milky Way. In this particular case, in this very extended stream from that is called GD1, it's probably a progenitor that is a globular cluster and not a dwarf galaxy. In this case here, the so-called orphan stream, which you see here superimposed on an all-sky view of RLI stars. There are many regions in which RLI stars still have to be searched for, but in others they have been detected. This blue stream here is called the orphan stream. It probably comes from a low mass dwarf galaxy, relatively low mass, as you can see here based on the metallicity distribution functions work done here in Heidelberg. The progenitor was probably a very low mass dwarf spheroidal galaxy that contributed these stars. The progenitor, however, has not yet been identified, as is the case for many of these objects. The Helmi streams would yet be another example. When adding both kinematic information and chemical information, we can get constraints on the possible progenitors of the streams. Remember the earlier cartoon of alpha over Fe versus Fe over H, here shown alpha as magnesium, where we have a turnover that happens already at lower metallicities. The stars belonging to the Helmi stream are indicated here in red. Overplotted are also stars belonging to certain dwarf galaxies that survive until the present day, such as the green points here, that is the sculpted dwarf spheroidal galaxy. Based on the similarity in this diagnostic diagram, one may suggest that the progenitor of the halo Helmi streams was actually a galaxy with a similar mass of Sculptor, of this surviving Sculptor dwarf spheroidal galaxy. So one has some constraints also from the chemistry on the properties of that progenitor. Now, this is my last slide where I'm summarizing recent information that we obtained for the merger history of our Milky Way. And here is a suggested contribution of both in situ star formation as well as stars contributed by merger events as a function of galactocentric distance in radial direction, going out along the disk plane essentially, and going perpendicular. That's the Z direction that you see over here. Here we have always the relative fraction of different contributors. We can already see Gaia-Enceladus, or the Gaia Sausage event, was a pretty major event. It contributes a large fraction of stars at certain galactocentric radii. At larger distances, beyond, let's say, 30 to 40 kiloparsecs, its contribution is not so pronounced anymore, but here Sagittarius becomes a major contributor. In the innermost regions, however, we have a prominent contribution in these models also from in situ star formation. That's the light blue regime here, where we have the in situ halo and the in situ disk stars. We have additional smaller merger events indicated over here, which contribute in different ways at different radii, but not as substantial as these rather massive events such as Gaia Sausage or Gaia-Enceladus and Sagittarius. The inner galactic structure that I mentioned is so recent, it is not yet included in this plot. Overall, the idea is based on Gaia results for the merger history of our Milky Way in combination with ground-based spectroscopic surveys and photometric surveys, that in the inner regions of the Milky Way, both in radial directions and perpendicular to it, we are dominated by stars that formed in situ, but we also have appreciable contributions from accretion events in the outer regions, in the outer halo of our Milky Way. Almost everything comes from accretion events. So that would be the current picture that we have for the merger history, to a large extent, thanks to the very detailed information that Gaia is enabling, where we finally have the option of disentangling in situ stars and stars from accretion events. Also, kinematically, we can get very clean diagrams for the contribution from accreted objects and then try to infer their properties. And that brings me to my summary slide, which I will just put up here since my time is up, and I leave it for you for the questions if you want to know anything more specific about these subjects. I should point out, stay tuned for more discoveries. Gaia data have been available for a relatively limited period of time. They are continuing to improve in quality. In the coming years, we will undoubtedly further refine the picture of the accretion history of our Milky Way. Thank you very much.
Well, thank you very much indeed, Eva, for a very beautiful and very colorful talk. And my applause should be multiplied more than 100-fold for all the others who cannot switch on their microphones. So to the audience, as most of you know, you can ask questions in the chat, type in your questions, or you can raise your hand, and then we will try to read and let you speak as you like. So Willy Wefler, our computer manager at ESA, will switch on microphone. So I see one hand by Timothy Bears. Willy, can you switch on Timothy?
Okay, I think I'm good.
Yes.
Okay, great. So Eva, wonderful talk. It is a challenge, as you know, even reporting the most recent results. But I think especially for people who haven't, like yourself, worked in this field for a very long time, it's very tempting when one gets great data, like from Gaia, to forget the history in certain areas that people working with much poorer data were clever enough to interpret. And one example, for example, the Horta et al. Argument about the massive accretion in the galactic center leading to old metal poor stars. There is evidence going back to Preston et al., 1994, I believe it was, based on relative ages of horizontal branch stars, that such an ancient structure may well exist. They wouldn't have interpreted it at that time. But that was indeed confirmed by Santucci et al. In 2010, I think it was, and then Carollo et al. There are detailed maps, one on the cover of Nature of Physics, which basically shows what those authors called the ancient chronographic sphere. And so you can't get much closer to calling, the accreted events that Horta et al. Sees with great data. Doesn't really differentiate itself in any nominal way or obvious way from previous discoveries. So there is an issue that people should try to keep in mind as we go forward, that this is a continuum of interpretation, not just a single discovery. I just thought I'd point that out.
Yeah, you're absolutely right. And that also holds for other discoveries. If you consider, for instance, the Schuster and Nissen stars and Gaia-Enceladus, I mean, indications existed already for quite a while.
Right.
Basically, this picture continues to develop. it is not something that is unique and only now possible, but it has been existing for a long period of time. Moreover, it's not just that you had the chemical information in some cases it was purely photometric information, say purely over densities that were discovered, and for which we can now add detailed kinematic information and chemical information. So it's a continuing picture, an evolving picture.
Let me read some questions from the chat. Craig Heinke asks, the Sagittarius mass is given as 2.5 times 10 to the 10 solar masses, while the inner galactic structure was given as 5 times 10 to the 10 solar masses, yet the IGS was a more massive accretion event. Maybe I'm missing something.
Yeah, it depends very much on which mass estimates you use. I should point out the mass estimates are actually rather uncertain in many cases. And it always is also a question of whether the total masses are meant or whether people use the stellar masses and whether they use the present day masses or whether they actually use the rather hypothetical masses at accretion. So different authors operate often with different mass estimates, even for the same time periods. When they talk about what was the initial mass of, let's say, Sagittarius, there is quite a bit of uncertainty. And it depends then on what mass that particular study has chosen for its comparison. One has to be a little bit careful. It's not really, at this point, as absolute a scale as we would like to have. Similarly, for the mass of the Milky Way, even the mass of the Milky Way, if you look at the literature, you find quite a range of different mass estimates. So it's a bit dependent on which one you pick in order to draw your conclusions and to come to such statements of this is much more massive than that one.
William Wall asks, if encounters of the Sagittarius dwarf resulted in small bursts of star formation, do you see similar effects from encounters with other dwarf galaxies? If not, why not?
So in the case of Sagittarius, this recent study suggests that it is visible in the star formation history of the local disk. For other dwarf galaxies, it seems that especially for these low mass dwarf galaxies that contributed to the buildup of the halo, their individual masses would have been so tiny that they had hardly any effect on the Milky Way. In particular, they would not have affected the Milky Way's star formation history. At early times, when the accretion happened, effects may in principle have been even much larger than these peaks that we see today, especially if the early mergers involved relatively massive galaxies that were also gas-rich. Because if this gas was accreted also, that gas could have led to enhanced star formation at the time of accretion in the Milky Way. So that is something that we do not see today. Sagittarius basically just triggers or seems to trigger star formation when it orbits around the Milky Way. The gas is no longer involved, it no longer contains gas, but at early times also the gas that was contributed may have had a considerable effect if those galaxies were sufficiently massive.
Hans Zinneger asks, hi Eva, nice to hear from you from far away in Chile. My question is about the many globular clusters that were accreted by the Milky Way. In these minor merger events of the Milky Way with a dwarf galaxy such as Gaia-Enceladus or the Sagittarius dwarf, how are these accreted globular clusters different from the in situ Milky Way proper galactic globular clusters? Are they more metal poor? There is a metallicity gap dichotomy between globular clusters, isn't it? Gracias, Hans.
Basically, that is the idea that if you look at this diagram where we have age versus metallicity, that the accreted globular clusters would differ from in situ clusters by being more metal poor at the same age. So the in situ globular clusters, which presumably are the ones located over here in this pre-Gaia plot, at the same age are more metal rich than those globular clusters that presumably were accreted, and they have lower metallicities, even though they have the same age. And the assumption, the underlying assumption, when one makes this chemical argument, is that the globular cluster metallicity traces the host galaxy metallicity at the time of the formation of that globular cluster. That's the underlying assumption. If you then assume a mass metallicity relation, you would have lower metallicity globular clusters forming in lower metallicity and lower mass dwarf galaxies. Then you would have in higher mass galaxies, which would then also be more metal rich. That's purely a chemical argument. The Gaia data contributed here orbital information for these globular clusters. And the orbital information associates then a number of these objects with, for instance, Gaia-Enceladus, like this idea that maybe 27 globular clusters were contributed by that event. Or they associate globular clusters with Sagittarius. The most prominent 4 globular clusters that I mentioned earlier in the early press release for Sagittarius were known already at that time, or believed already at that time to be associated with Sagittarius. So that is not a Gaia result, but subsequently additional globular clusters were added as possibly having come from Sagittarius. And similarly for other merger events, Sequoia, for instance, which presumably also contributed globular clusters. So their kinematics would be added to the chemistry.
Olivier Talagrand asks, how is merger of galaxies compatible with the expansion of the universe, which says that the distance between galaxies increases? Is it that galaxies that are close to each other tend to merge, while galaxies that are far apart separate further?
Precisely, that is exactly the answer. So only galaxies that are relatively close to each other will be able to merge in principle, because their mutual gravitational attraction and their short or small distances are sufficiently small to enable interactions. As one example, we are falling, our local group of galaxies is falling towards the Virgo cluster. And yet the idea is we will never fall into the Virgo galaxy cluster because of cosmological expansion. We have a motion towards that cluster, but we are too far away to ever be able to merge with that galaxy cluster. However, in our future, actually in our local group, we have other galaxies that are sufficiently close that mergers will occur. And these are not just the Magellanic Clouds with which our Milky Way might merge in the future. This is actually the much more massive Andromeda spiral galaxy, which is the second massive galaxy in our local group. Andromeda and Milky Way are the 2 most massive galaxies in the local group. Both are spirals. They are moving towards each other. And their mutual attraction, their motion towards each other, their distances are sufficiently small that they will eventually merge in spite of cosmological expansion. So within that small bound volume that we have here, interactions and mergers can occur. At larger distances, it would be difficult because of cosmological expansions. So in the future, we will merge actually with the Andromeda galaxy.
Peter Jediger asks, any hint as to what the original object that became the Milky Way looked like before any of the accretion processes occurred?
Not from these kinds of observations. I suppose that here the only hint that we would have is to turn to the high redshift universe and to look at galaxies that are observable at those very high redshifts. They're usually not believed to be Milky Way progenitors, but we do see galaxies at redshifts of 7, 8, 9, 10. And presumably our Milky Way would have looked at these early times similar to those luminous blobs with ongoing star formation, presumably with some rotation that then led to the formation of disks. We have at redshift 2 galaxies that look disky already. They have lots of rather massive clumps in their disk where starbursts are happening, possibly leading to the formation of star clusters. So that is the possibility that our Milky Way at earlier times looked like these galaxies that we see at higher redshifts. We cannot tell from Gaia observations. We would then have to turn to the higher redshift universe and try to make analogy arguments.
Let me read two comments on the chat. One by Margarita Rosado Solis. Congratulations, Eva, for this quite interesting talk revealing the so intense merger activity of our Milky Way. And one by John Gallagher. Interesting talk with great job of presenting information on the slides.
Oh, thank you.
Now a question by Friedel Thielemann. In the early part of your talk and close to the end, you referred to the alpha over iron as a function of iron over H, which is clearly related to star formation efficiency and the related kink when type 1a supernova came in. But how do you explain different magnesium over iron with an identical initial mass function?
Whether the mass function was really identical, that's an interesting question. We do not yet completely know whether that's the case. That's a slightly different topic, but I should point out that in a number of dwarf spoided galaxies around the Milky Way, very deep HST data have suggested that their initial mass functions may have been more top-heavy. Now, those kinds of statements are somewhat uncertain because we are dealing with very old populations, so the observable mass interval is relatively small, but it suggests that the mass function may actually have been slightly different. However, in this particular plot, the mass functions could play a role, indeed. They would alter the appearance of the plot. There's actually an upper portion of the plot that I cut out where that is shown. If you have a mass function that is dominated by very, very massive stars, in principle, you could have an even more extended plateau, because in that case, massive stars could contribute even more to the early enrichment. You would end up with higher and higher metallicities before eventually lower mass stars set in. So the appearance of this diagram would also be changed. You can have the same effect if you have just very efficient star formation, where little of the formed metals get lost, where you have a deep enough potential well to retain the metals to use them for subsequent star formation. That is the usual interpretation that we use here, where we say this kind of a plateau would indicate a deeper potential well. More enrichment could happen before the onset of supernovae of type 1a. And note that AGB stars and others are totally ignored in this simple-minded argument. Whereas here we would have a more shallow potential well. And for instance, more of the formed metals might have been lost from the system due to supernova explosions and stellar winds.
Ricardo Schiavone has raised his hand. Willi, can you please open him? He writes in the chat, he's a co-author of the Horta et al. Paper and would like to comment on the points raised by two of the attendees. Ricardo, please.
Thank you very much. Thank you, Eva, for a great talk, great review. I really appreciate your attention to all this work being done before. So I just like to comment on what Tim Beers has pointed out regarding the possible association of the IGS, which you call Heracles, to other evidence pointed out before by previous works. The issue here is that, given the high degree of uncertainty of the metal poor content of the Milky Way within 2 to 3 kiloparsecs, it is extremely difficult to associate a system identified on the basis of chemistry and dynamics with, for instance, populations which were identified on the basis of, for instance, of RI-Lyra characteristics or others. So we are really scratching the surface when it comes to the inner halo. And by inner halo, I really mean the innermost part of the halo within 3 kiloparsecs of the galactic center, which contains, by the way, almost half of the entire mass of the halo. So we don't really know what's in there. And as Eva pointed out, the mass of the IGS, of Heracles, is highly uncertain. We don't even know if it's the only accretion that, it certainly was not the only accretion that happened to be found there right now. There could be other systems that were accreted at lower masses. So we are really still just scratching the surface. So that said, we apologize for not having referenced perhaps other work done in the past, and we'll be very happy to reference it in the future if team would contact us with those references. Appreciate that. Thank you.
Thanks. Question by Robert Zinn in the chat. Gaia has also confirmed that the kinematics of the metal-rich globulars are consistent with membership in the thick disk, confirming that they were not accreted, unlike the majority of the metal-poor ones. The idea of globulars being a combination of accreted and in situ has a long history, does it not?
Yes, indeed, it does. Going back to CERN and Zinn, among other things. Yes, indeed. And basically, I would say in a number of ways, that scenario is rather nicely supported now by this combination of kinematic information plus chemical information and age information, of course. So that works out rather nicely.
Two more questions in the chat. Jiatong Fu writes, thanks Eva for the nice review. I have a question on the star formation history of the Milky Way. In the star formation history figure you show in the earlier slide, one relatively big starburst happened about 6 gigayears ago. If it was triggered by Gaia-Enceladus, why it is 2 to 3 gigayears after the merger? Some works conclude that the thick disk star formation is triggered by Gaia-Enceladus. Could you please comment on that?
A plot of the star formation history of the Milky Way. I'm not sure which one that was. You are not referring presumably to the plot that shows the impact of Sagittarius on the local stellar disk, because that's the one that I remember. You must be referring to some other plot of star formation history. It's not this plot here, I suppose.
He writes the 2022 work.
2022.
Maybe Billy, we can switch him on. Zhao Ting, can you raise your hand again, please?
Oh,
yeah.
I'm sorry. This, of course, is not 2022. This is 2021. Sorry. 2022. Sorry, that's nonsense.
Okay, she's at the microphone. Yes.
Hi, Eva. This is Xiaoting. Many thanks. Yes, I'm referring to this a figure you put here. So I do see that there is a relative big star formation around 6 gigayears ago. Right. This one. So I, as my understanding, at this time, it may be tricked by Gaia-Enceladus merger. But my question is why it is about 2 or 3 gigayears after the merger.
So here, the authors do not make any argument related to Gaia-Enceladus. They purely make the argument that this is caused by the pericentric passage of Sagittarius. So this is the star formation history of a 2 kiloparsec sphere around the sun, very local. And they argue that this is because of the repeated pericentric passages of Sagittarius, not Gaia-Enceladus, which is much more further in the inner regions of the Milky Way.
Thanks. My another question, second half of this question is, some works conclude that the Gaia-Enceladus triggers the star formation of the thick disk. Could you please comment on that?
Yes, that idea was suggested, I think, already in the early discovery paper by Hilmi and collaborators. And I saw that there were a number of different arguments in the literature. There were, for instance, or there are very nice simulations by Grand and collaborators, which come up with a nice scenario that supports this. And they also argue that if it was a gas-rich merger, it would even have triggered star formation in the Milky Way. There is another paper, which is the one with the astroseismological ages, where the argument is being made that the thick disk may in part have already been in place prior to that merger. So there's some argument of how important Gaia-Enceladus was for the merger, for the formation of the thick disk. But most of the recent articles that I saw supported the idea that that particular merger may have been actually rather defining in creating the thick disk, puffing up the thick disk. Now, those papers were all written before the suggestion of the Horter et al. Paper of the IGS. So that has not yet been included in any of these studies. If the IGS was indeed more massive, then of course that would also have had an effect. So I think this picture may continue to evolve and may continue to change in the coming years. But the idea in any case would be there was a pre-existing disk that was heated due to that merger.
Thanks.
Let me read the last question on the chat. Andreas Pala asks, seeing that most of the stars in the halo are older and stars in the disk seem to come from satellite accretion, is it possible to somehow estimate the probability that our sun originates from an accretion event?
So a lot of the stars in the halo, if not the majority of the stars in the halo, especially in the outer halo, probably come from accretion events. In the inner regions of the Milky Way, instead, we have a large proportion also of in situ star formation. So basically, here in the innermost regions, we are 8 kiloparsecs from the galactic center. We have a large fraction of in situ star formation. We do also have, of course, a large fraction of accreted stars. It's only in the outer regions where the accretion really becomes dominant. Whether the sun comes from an accretion event is an interesting question as such. I would say chemically, the sun is not really peculiar. It has been hypothesized, actually, that's a totally different line of argument, that it might have been related to the open cluster M67 in some way and might have formed there. That the sun as such was accreted is an idea that I have not really seen. Chemically, I would see no need for that. And dynamically, I would see no need for accretion, an accretion origin of the sun. I would say that basically we could assume that it formed in situ.
So there are no more questions in the chat. Let me announce next week's talk again. Sabani Basu from Yale will talk about, do we know what the sun is made of? The puzzle of the solar composition. And before we thank Eva again, I'd like to thank Willy Weffler and Andrea Fischer and the ESA staff for helping make this happen. And Eva, thanks very much again. There are still lots of very nice short thanks in the chat to you for a nice talk. And again, we still have more than 60 participants listening to the question and answers. Thanks very much indeed for a wonderful talk on the history and present time of the merger history of the Milky Way with Gaia. Thank you very much.